Right, so in this drawings tutorial we're going to try and recreate the simple part drawing that you can see on the screen here. There's a few techniques in this to do with storing tolerances inside the part model itself that may be a little bit beyond your sort of basic part drawings. And then there's a little bit to do with importing model items, so these whole callouts, and how you might modify whole callouts. We'll also drop into a little bit of setup of the sheet format itself, so you can see that there's some values in here. We might talk a little bit about where those values have come from, because again some of those are actually linked to custom properties inside the part itself. So yeah, let's get started. So we'll just have a quick look at the part that this drawing's been driven from. So this is the part as it's modelled, and what we're going to do is, you can see it's primarily a part that you would manufacture on a lathe probably. So it's primarily just a simple revolve. So the majority of the actual geometry here is generated with this revolve feature at the top of the feature manager there. So we're just going to drop into the sketch that generates the majority of that shape. Just zoom in a little bit. And what we're looking for here is any values that have tolerances on them already. So you can see there's two values here that have a specific tolerance applied to them. You can also see that we've actually used a specific fit. So this is an N7 fit for this internal bore, and this is an N9 fit for this internal bore as well. So what we're going to do is we're just going to quickly look at how you would set that up. So I think we'll use this 27mm diameter as an example. We're going to return it to no tolerance when we've finished, but we'll use it as an example of how you would set up a tolerance on any dimension on a drawing or on a sketch, sorry. So let's say we wanted to apply a specific fit to this 27mm dimension here. So you would select the dimension itself. You don't want to edit the actual value, so it's easier, rather than clicking on the number, if you click on one of the arrow leaders, and then what you see on the left hand side is your property manager for all the properties to do with that particular dimension. Now, we've already said that we want to modify the tolerance on this, so you can see there's a specific section for tolerance there. And then tolerance type is currently set to none, which is what we can see here. It's just a plain value. So what we're going to do is we're going to change this to some of the other options here. We're going to look at some of the options. So there's a basic, which basically just puts the rectangular box around your dimension that marks it out as just a basic dimension. That's not particularly useful for what we want to do when we want to put an actual tolerance on this. You can put a bilateral tolerance where you can manually specify the plus and minus tolerances on the actual value. So you can have different plus and minus tolerances like that if you have a specific tolerance plus range and tolerance minus range that you want to apply to that. There's the limit option, which basically takes these values that I've typed in here and it displays them as two values for the dimensions, so an upper limit and a lower limit. So it's taking these values and it's either adding them or minusing them from the original value, the typed value. So if you see, if I go in here, the typed value is still stored there. So the 27 is still stored, and if I wanted to edit that, I would edit the 27. So let's say we want to drop it down to 26 nominal size, and then what the system does is recalculates what that 26 nominal will be when we add the 0.1 on, or minus the 0.05 from it. So that's how the limit option works. So let's go down the list and use some of the others. Symmetric, it's basically the same functionality as the bilateral, but you can only enter a single value, and that will be both plus and minus. So that can be quite useful. Minimum, again, that's just an annotation basically. So that just takes the value that you've typed and it indicates that that's the minimum value. So not as useful really. Maximum, exactly the same operation, it's just that that's the maximum value. Now the one that we're going to use, these three at the bottom here, are to do with predefined fits. So as we've already said, we're using an N7 fit here and we're using a H8 fit here. Now if you have the manual tables, maybe in a pocket book, a lot of engineers have a reference book that they have all the fits listed in. The nice thing about SolidWorks is it has all that data stored within the SolidWorks installation. So if you know what fit you want, you can pick it from a list that pops up. So I've selected fit as the tolerance type, and given that this is a bore or a hole, it's going to be in the drop down list that define internal diameter fits. So that'll be hole fits or internal bore fits. There's a whole other list of fits that apply to shafts, so that would be an external cylindrical face. We may put one of those fits on a dimension like this. So you've got to make sure that you're using the right library of fit types. Are you applying the fit to an internal hole or is it to an external shaft? So let's see what we can do in here. So let's scroll down to quite a common fit. A H7 would be quite common. So if I select H7 from the drop down there, it just puts that in as an annotation. So the assumption there will be when you print the drawing with this H7 fit on, the engineer which is the engineer that is manufacturing this part knows what a H7 fit is going to be in terms of plus and minus tolerance for a 27mm internal bore. Now that may or may not be the case, and the way that your machine shop or your manufacturing department is set up, that might be absolutely fine. But what you can actually do in SolidWorks when you've chosen your fit is you can ask it to list the fit and the tolerance that that fit entails at that actual size. So the way that these fits work is the plus and minus values vary depending on the actual nominal size of the dimension itself. Other things to note in here, fits such as a H7 fit at this sort of scale, it might be worth listing it to 3 decimal places. We're using millimeters here, so you can do that down at the bottom here. Unit precision for the tolerance is set on 2 decimal places at the moment. If you want it to 3 decimal places, the fits are normally, if you look them up in a reference textbook or a reference handbook, they will be listed to 3 decimal places, especially at this sort of scale. So again, it will depend on your manufacturing department what sort of accuracy they can achieve. But yeah, just be aware that if you show them at 2 decimal places, or even worse at 1 decimal place, you can see it's rounded to 0 there, which is not particularly helpful. So yeah, 3 decimal places I would say is probably the most trouble-free setting. 2 decimal places possible. So yeah, fit with tolerance. The last one there is just tolerance only. So you don't make the machinist aware of what fit you've used, you just list the actual tolerance that that fit creates. So, but yeah, fit with tolerance is a very useful one. So that might be the one that you use most often, unless you want a specific custom tolerance that isn't defined by a particular fit. So yeah, that's how you would set those values. So let's switch that 27 back. Well, no, let's leave that 27 with a tolerance and fit on it. So we've made a modification to the model. And you needn't think that these only have to be applied, or tolerances only have to be applied to cylindrical dimensions, so dimensions that are defining a diameter. You can apply them to linear dimensions as well. It's just that in terms of limits and fits, linear dimensions don't really get the same limits and fits as actual shafts and internal hole sizes. So normally what you do, let's say if I wanted to put a particular tolerance on this value here, so I keep by mistake clicking on the actual number itself. I should be clicking on another part of the dimension. Let's put a bilateral fit on that of plus 0.05 and minus 0, minus nothing. So yeah, you get the idea. You can apply tolerances to various different values. So that is the recommended way of managing tolerances within your part. List them in the actual part itself, if possible. It's not always possible, but a lot of the time that's the best way to manage the storage and the sort of documentation of the tolerances that you want. You actually model them into the part itself. So a quick one now. What have we broken there? So let's see if we can fix that. It's having some sort of issue. For some reason it's lost the reference axis for that circular pattern. It may be because we messed around slightly in the sketch and something has changed its reference name, but that's okay, we can fix that. So there you go, the part's back as it was. So there's a little postscript to what we've just done there, which is we were working in a sketch and we've just seen how you would apply a tolerance to any dimension in a sketch, so we know how to do that. Now you might say, well, what if I've got an extrude and I want to apply a tolerance to the actual depth of the extrude itself? So it's not, the dimension isn't listed in the sketch. It's actually the depth value that I entered for the extrude. So let's quickly just create a dummy extrude here so that we can see how that might work. So all I'm going to do is just quickly sketch on this back face of this part and just quickly make a little boss. So I'll give it a dimension and OK the sketch, extrude it as a feature, so there it is. So I've extruded it by 10 mil. Click on OK. So let's say I want to put a tolerance on the 10 mil. Now what I need to do is make that 10 mil extrude value visible, and from this part that I'm looking at, there's two ways to do that. I can click on any of the faces which are unique to that feature that I've just created. So that face would work on the end, or that face there would work as well. And what you can see, hopefully, when I click on those faces is that the extrude value becomes visible. So that's all you need to do. Now if it's not easy to do that within your model, to click on some unique faces that are only part of the extrude feature that you've created, you can just select it in the feature tree over here. So if you click on it there, the same thing happens. And you can see that extrude value appears, and you can edit that in exactly the same way. So if I click on one of these extension arrow lines, and then what happens is that dimension, it just regards that as a normal dimension. It's just that you don't access it via the sketch, you access it via the actual feature itself. And then you can see if I want to put some bilateral tolerances on there, I can put a bilateral tolerance on in exactly the same way that I did before. So yeah, that's the way that you would do it on a dimension value which isn't part of an actual sketch. So pretty similar to what we did before. So we'll just delete that. We don't need that feature for the next part of our drawing setup. So yeah, so we've done the setup steps as we were modeling the part. We've created the sketches and the dimensions with the tolerances that we intend to apply within the drawing. So let's go back to the drawing of this thing now. So what we're going to do, I think, is we're going to put a second sheet into this drawing, and we're going to try and recreate what we're seeing on this sheet, on the first sheet. So let's see if this works. We'll put a second sheet in. I think in this case, because these drawings were created on a separate system that had a specific sheet format, what we're going to have to do in this case is take a copy and paste of this sheet so that we get all the format and setup, and then we'll just do a bulk delete on everything so that we can recreate it. So you wouldn't have to do that if you set up the drawing sheet formats correctly on your system. But as I say, these drawings have come from a different installation of Solidworks, and they haven't been saved out with the sheet format as a separate file. So this system is quite rightly saying it can't find that sheet format. So that's why we've done a copy and paste of that first sheet. So a few little housekeeping things first. When you do a copy and paste of a sheet, you don't always get the name for the sheet that you want. So if I want to change this to just sheet 2, I'd right click on the sheet tab there, go down to rename, and then just overtype the actual name that I want for this sheet. Next thing, let's drop some of these views in quite quickly. So we've got what I'd call the front view of the part here. So I'm going to try and find that in my view palette. So if we go up here to view palette, the view palette needs refreshing. It's saying here view palette's out of date, so I'm just going to quickly refresh that. Make sure you've got the right part selected there. If you've got multiple parts open in Solidworks, it might not be the part that you want to put on this drawing. So yeah, which one is it? It is, I think it's this one, or maybe it's this one. Let's have a look, see if we can spot the right view. I think it is that view. It's the what the system's calling the back view. So I just okayed that view there. I didn't want to project any other views from it, so I just clicked on the green tick. So is that the correct view? It is the correct view. And we can double check that on this sheet. If we select that view, see which view it's using here, it is using the back view. So there's the back view. So next view that we're going to put in is this cross section. So you can see there's a cross section line there. So if we go up here to drawing, or in older versions of Solidworks, I think it's called drawing views maybe, but it's the tab to the left of the annotations tab. Section view is what we want. Now the section line was a vertical section line, so we're going to want to select that over here, and this line wants to snap itself to various pieces of geometry if you let it. So I want to snap it to the center point of all these circular edges, so I'm just going to click there. Now I don't want to modify the line particularly, so I'm going to just click on OK. Then under my mouse pointer I get the cross-sectional view as it's going to be from that cross-section line. I can just click and drop that. A few things here. I think I'd rather have this named as A, seeing as it's the first view. So if I go up here, whilst I've still got that cross-section view selected, I can overtype with the letter A. Now it's picking me up on that because it's picking up that I've already got a sheet 1 with a cross-section A in it. So maybe we'd leave it as C. Or maybe we'll choose something from the end of the alphabet instead. Maybe we'll call it X, so that we don't get any conflicts with the first sheet. We're using the opposite end of the alphabet. So anything else to note about that first sheet? We've got a 3D view up here. Let's drop that in as well. So if we go to our view palette, the way I like to set my 3D views up, you can save a predefined viewing angle in the part itself. That's a totally valid way of doing it. The way that I tend to do it is just on the fly, is just drag the current view into the window and then use the 3D drawing view tool to then align that view as I want it. So maybe something like that. The general rule of thumb there is you want to show as many of the features of the part as you can and give a sense of for want of a better word, 3D-ness of the part that you don't get in these 2D views. You have to sort of use your imagination with these. So yeah, that'll do for our purposes there. So I'm thinking maybe the sheet scale is slightly different on the first sheet. Oh no, it's the same. I thought that these views looked slightly bigger. So let's start putting some of these annotations in. Now the first thing that I'm going to do is I'm going to insert these two hole callouts. Now there are a couple of ways of doing that. One is you can insert them as a hole callout. So you pick the hole callout option there and you attach it to the hole, and you should get some sort of description of what that hole is. The other way that you can do it is you can import it as a model item, and I think that's the way that we're going to do it here. So let's go to sheet 2. So I've already said we're going to import it as a model item. If you want to read the tooltip that pops up there, imports dimensions, annotations and reference geometry from the reference model, so that's the part file, into the selected view. Use the property manager to customize the model items that you want to insert, is the end there. So model items. What do we want to insert? We want to insert a hole callout, so that would be that little icon there. So by default, normally when you come in here, it's marked for drawing dimensions that's selected. Now we don't want that, so I'm going to untick that, and then I'm going to click on hole callouts. That's what I want to insert. Where's the source for these? So you can try and select the feature that you want to insert them for. That's often quite tricky on these 2D views to specifically select just one feature. So I'm going to say entire model. I want you to bring in, so that's basically an instruction for the system to bring in all hole callouts from the entire model into, I don't want them in all views, I just want them in this view. So I'm going to untick that. Then it's saying what is the destination view that you want to bring all these hole callouts into. It's going to be this view here. So I've just clicked on that. Then I'm going to click on OK. And what should happen is any features, in this case holes, that are oriented in the right orientation, and in this case, because it's a hole, we need to be looking through the hole rather than at the side view of the hole, so that we can see down into it, should get a hole callout inserted for them. Now there's a few things here. If we go back to sheet 1, just to tidy the drawing up slightly and try and make it more legible, both of these hole callouts have been placed on the same side of this drawing view, whereas when we imported them in, because of the hole member of this 3-hole pattern, so these 3 holes are the same, they've just been patterned. Because of the hole member of the pattern that this one has attached itself to, that's not very possible. So I could put this annotation over here, but we're committing that cardinal sin of obfuscating, is that word? Obscuring too much of the drawing. So this whole call-out leader arrow is going across the center of the drawing, which we could make less obtrusive. So the way that you would do that is you just click and drag, try that again, on the little square on the end of the arrow there, and if you allow it to snap itself to another member of the same pattern of holes, it will happily keep the same hole call out but attach it to the other pattern member. So I couldn't drag this and put it on this other set of patterned holes because it's not the right call out for them. But I can drag it and put it on another member of its own pattern. So yeah, they're both on the same side now. If we want to have a look at these annotations a little bit, because of the standard that we used here, so let's go back into the part and just see the whole standard that was used. So let's interrogate this one first. What whole standard was used? Standard was GB, and these are counter board heads for a hex head bolt, an M4. And what are the other holes? They're an M4 tapped. What standard are they using? Anti-metric. So the reason that we're just having a quick look at this is the style of hole call out that you will get on your drawings will be affected by which one of these international standards you pick to create the hole. So obviously for metric holes, there's a lot of different metric standards in here. Obviously anti-metric is obviously metric. BSI has some metric sizes. ISO, DIN has metric sizes in it. Some of the others are metric as well. And if you want to have a play around in your own time with those and see how that affects the text that you get in your hole call out, then that's quite a useful thing to just be aware of. But the text that we've got here, so let's interrogate a little bit of this. So what are we getting in this particular hole call out? We're getting a quantity of pattern members is the first thing. So that's quite useful, because if I was to go back into this pattern and increase or decrease the number of pattern members, that value there is linked to the pattern itself. So you can see that in the dimension text. It's this option here, number instance. So if I would just want to play around with this hole wizard text and just illustrate what's possible. So what I've done there is I've put another line in down below. If I click on callout variables, count is one of the options in there. So often on a drawing you'd have the number of instances of a patterned item, and then you might write PLS after it for places, or it's in 3 places on this drawing. So you can see there, the places is a standard typed note, but the 3 is actually linked to the pattern itself. So that might be quite useful for you. I'm going to actually undo that because we've already got that information listed at the top. So we've got a little X that's typed there. Again, if we go back in and interrogate this, the X is a static value. The number of instances is a dynamically linked value. The diameter there, that little note there, mod diameter, is just that diameter symbol. So SolidWorks refers to that as mod dash diameter. Through all, again, is a dynamic value that's linked to the hole itself. So when the hole was set up in the SolidWorks part model, the through all option was selected. Now if we went back in there and changed that to a specific depth, that through all would disappear, and it would actually give us information about the drilled depth. So that was the pre-drill. There is the tap. The tap's also going all the way through, and again, these values are dynamically linked to that hole wizard hole that was inserted. So if we changed it to say an M5 or an M3, that would auto update. The fact that it has a countersink on the mouth of the hole itself, that's also dynamically linked. The size of the countersink, the angle between the countersunk faces, and the fact that that countersink is on the near side of the hole. So it's on the side that we're looking at here, or it's on the side of the hole that you as the user selected as the face of the model where the hole begins. So you can countersink the far side of the hole, and if we did do that, this hole callout would change to reflect that. So the hole callout, as much as possible, is dynamically linked to the hole and the pattern. So that's the way to set these things up. You don't want to be manually typing anything in if you can avoid it. 1, because it's time consuming, and 2, because it's not then dynamically linked to the model. So as if to prove that, let's just temporarily change the number of pattern members in that model so that we can just test that that is actually working. So let's put 4 of these things in. So we'll bump that up to 4 if it'll allow me to do that. Now why is that not working? Let's try that again. Should have 4 pattern members. How about 5 pattern members? Maybe it's because this thing needs saving. Now that is quite odd. It's because this pattern has been set up with the pattern spacing as the drive in number of degrees. What I'm going to do is I'm going to say I want equal spacing around 360 degrees. So yeah, took a little bit of investigating, but we got there in the end. How about, I'm trying to not get these holes interfering with the other holes, but I don't suppose it matters. 9 pattern members. Let's change it to 9. Let's go back into the drawing, check that everything's updating. Yeah, we've now got 9 pattern members there. So that was only to illustrate that that is actually the case. So these holes are these hole callouts are dynamically linked back to the actual patterns that are driving them. So back to what we were doing. So we put the hole callouts in. The hole callouts have been inserted as model items, so that's the best way to do them. It means that they're dynamically linked back to the patterns that created them and the hole wizard features that created them. What we're going to do now is we're going to put those tolerance values in this cross-sectional view. So those values that we toleranced in the sketch, which is driving this revolve, we want to put some of them in this actual drawing view here. So again, we're going to click on model items. What do we want to import this time? We don't want to import hole callouts, so we're going to deselect that one. But we do want to insert dimensions that have a tolerance on them, and that would be that icon there. So toleranced dimensions are what we want to import. We want to import them from the entire model. Yes, that's correct. We don't want to import them to all views, so we're going to deselect that. We do want to import them to this specific view, so you can see that that gets entered in there. Then we'll click on OK, and you can see it's brought them in. So all I have to do now is space these out as I want them located. So we'll just drag them to wherever we need them. Let's put that one a little bit further out. Yeah, you get the idea. You would spend quite a bit of time getting these looking as you want them to look. So there's the tolerance values. And then obviously you can use that insert model items to bring in non-tolerance values as well. It's just that you then have to have created the sketch using the exact dimensions that you want to use on the drawing. And what I mean by that is, let's say when you create the drawing you want to put an overall depth dimension from this edge here all the way back to that edge there. But let's say when you're creating the sketch, putting that value in is not as useful as putting some chain dimensions in from here to this face, and then from this face to this face, and then from this face to this face. So in that instance, the way that you want to dimension the drawing isn't always exactly the same as the way that you draw the sketch, because the two have different pulls or different constraints on how you dimension them. So sometimes you can import all the dimensions. You can use a combination of the ones that you've specifically marked for the drawing in the sketch, or just all dimensions. You can import them all. So let's see an example of that, even though we're not going to use it. So you can see it's brought them all in there. And you could do that. You could delete the ones that you don't want and keep the ones that you do want. But in this instance, I think what we'll do is just manually dimension up this drawing view now. So we just use the Smart Dimension tool and start manually adding dimensions on here. So let's put an example one on there so you can see that would be the overall one. So yeah, you can use a combination of the two methods. Either importing the model items in, which is quite useful for toleranced values, as we've already seen. And the reason that you would tolerance the part model and not tolerance the drawing is that wherever possible, the part model should kind of drive all the downstream activities that you want to do, essentially. So that's create drawings, create CNC programs from the parts or from the assemblies. Wherever possible, try and store as much data inside the parts themselves as you possibly can. So let's have a quick look at the rest of this. As it happens, we didn't have a dimension that governed the entire depth of this part. So let's put some of these other dimensions in. Let's put these angular ones in. That should be relatively easy. So we'll go back to sheet 2. Now because these holes, these larger holes, these count bore holes, are part of a circular pattern, the system's taken the liberty of putting this collection of center marks in. So I'm highlighting it in orange. And those center marks have angled center lines that go through those counterboard holes that reflect the fact that it's a circular pattern. So they're all angled towards this center point. Now that's quite useful because what I can do with my Smart Dimension tool now is pick one of the lines that's running directly through the center of this hole. So picking the section line might not be the wisest option because that might move. So if I right click and click select other, let's see if I can find a line that line there, that center mark line that's got those two little blue squares on either end of it. That would be useful. And then pick this one here. I get a dimension between those two. I can then drop that dimension, and then I can do that again on this dimension here. And you can see if I try and drag these two near each other, they want to kind of snap together. Just neatening them up slightly. I might drag that view off to the side. So what else can we pull out of here? There's a chamfer dimension in here that's got a manual 7 corners note attached to it. There's some diameter dimensions. Let's put this one in 21.3 from that internal wall out to the end there. So this is pretty easy stuff. This is just standard linear dimensioning, just like you would do in a sketch. You get the idea. That's not that difficult. So I think in terms of setting the drawing views up, yeah, let's put this chamfer dimension in as well and just talk a little bit about that. So chamfer dimension is a subsection of the Smart Dimension tool. So if we go in there, chamfer dimension is a specific type of dimension. And if we zoom in and look at these chamfers, there's the chamfer. Now what the Chamfer Dimension tool is expecting you to do is first click on the edge, which is the actual chamfer face itself. So that would be that face there, or that edge there. And then it's looking for a reference edge. And by that I mean an edge from which it can measure the angle that that chamfer has been cut at. So I could pick this edge here, or I could pick this edge here. So I'll just pick that one as an example. Then I can drop that chamfer dimension. It's running out of space down here, so maybe what I'd then have to do is rejig some of these annotations, or maybe put this dimension, delete that dimension and maybe put it in on the top of this view. That might be more sensible. But the problem is with this is there's no easy way that I've found to get a quantity of chamfers listed in here. So that is just a manual note that's been added. So I'm just hitting enter there and just manually saying, well, how many chamfers do I have in that feature? I've got 1, 2, 3, 4, 5, 6, 7. So that is just a manual 7 PLS under there for 7 places. Now that's not the best way, or it's not the way that I'd prefer to do that. What I'd prefer is to have the chamfer tool interrogate the model, and however many edges were clicked on in that one chamfer feature, that would be automatically entered in there. So that's not a dynamically linked value, that's a user entered note. But we've already talked about the risks of doing that, and the fact that when you just type a value in, if you then go back and change the model, that value doesn't update. So you've got to stay alert, stay on your toes, just be aware that that is the case when you're checking your drawings before signing them off. So I think pretty much we've replicated what we've got in this view there. Obviously there's some other dimensions there, but they're pretty easy to enter into the actual drawing. So I think what we'll do, we'll have a little quick look at the sheet format that's been used here. Not so much for the layout. So what I'm doing there is I'm just right clicking over it, editing sheet format, And then what happens is all my drawing views and dimensions temporarily disappear, and that's because I'm editing the sheet format itself. You can see all my drawing views are sort of grayed out, and that's because I'm editing the actual sheet format. Which, if you want to think about it, it's like a layer. It's a specific layer in your drawing. It sits before all the other layers, all the other views, and you can edit it, and then when you've finished editing you tell the system you've finished, and then it gets locked again, so you can't accidentally make changes to it without intending to. So what have we got here? We've got a few values. Now this one, the part number, as we're calling it here, is the actual file name that part that we were working on has been saved under. So the SolidWorks part that we saw that was driving this drawing view has been saved with the name PLA 1504. And what we've done here at the bottom is we've asked the drawing sheet format to import that name. So we don't ever have to type the name of the part file that is shown in the drawing. That will always auto-update. So again, it's keeping these links, these dynamic links, so that you don't have to manually enter these values. Now what we're going to do is replicate that, so I'm going to delete that out of that text box. So that's just a standard text box, just using the annotation and then note option. And then when you get your empty text box like that, and normally you would type some text in there, you don't. You set the font up that you want, and then you go over here to this button, link to property. And what this allows you to do is pull a specific property either from the current document, so that would be the drawing that we're working on, this drawing document, or the part document that is shown in the drawing. So we don't want to pull it out of the drawing document, we want to pull this information out of the part document that is shown in the drawing. So you would select this option, model found here. Model found here. Drawing view specified in sheet properties. Yeah. So that tends to be the first drawing view that you drop onto a sheet. That would refer to that. Drawing view specified in sheet properties. Then it confirms what that drawing view is showing. So you can see the SolidWorks file name for that drawing, for that part, sorry, is PLA 1501. So we can be reasonably secure that that's the right part that we've pointed it at. Then the next box down below is what property within that part do you want to enter into this box. So let's see what the options are. Now the one that we want is this one, SolidWorks part number, and then it evaluates that value that you've selected up here. So that's another check that you can perform. You can check that you've got the right value, but let's have a quick skip through some of the other things that we can pull out of that part file. So there's all things to do with drawn by, creation date, so you can see when the file was created. There's material that we're going to talk about in a minute. There's supplier, there's approved by, there's all sorts of things that you can pull out of there, out of the actual part document itself. And SolidWorks file name is the one that we're going to use. SolidWorks part number is acceptable in this particular part, but that it won't necessarily be visible in the parts that you bring in. So SolidWorks file name brackets file name is the one that's always there, always visible. So that's what we're going to put in that text box. Now let's have a look at some of these other values. So the way that these parts have been modeled, they've been saved with obviously a SolidWorks part file name that we've talked about. That's what's entered in that box. But they've also been saved with something called a description as well, and that's what's been inserted in this box. So if we, again, we'll delete the value in there, we'll go into file properties, we'll say it's the model found where in the drawing view specified, it's this model. And then within this drop down list of custom properties here, one of them is called description, and you can see a description of what this part is has been entered into the actual part document itself. Now we're going to look at two others here that have been entered. There's one here, aluminium, which again is not a typed value. Now you can tell whether these are typed values if you hover over them, and the tooltip that pops up, so it's just disappeared there, I'll make it appear again, has a $sign at the start. So you can see that has a $sign. So the way that you would read that is the $sign indicates that it's a property rather than a typed value that the user's typed in. So that indicates that it's a property, and the way that you read it is property sheet and then in inverted commas material. So it's a property that's been pulled out of the sheet. So let's delete and recreate. Delete. Model found here. Selected component. Yeah, it's the bearing housing. And this is a property that's been pulled out of the drawing sheet. Or is it? Now this is interesting. Let's see if we can find this. Here we go. Material. So that's just a property. And same with treatment. Now that all might be lacking from the parts that you are creating, and let's go and see how you would store that information inside your actual part model. So let's have a quick look at this part model again. So this part model has information stored within it that is additional to the information that you have in all your part models. So the default information, additional information has been put into this one. And the way that you do that, the way that you store information inside a part, is in the File menu, and then Properties, and then the Custom tab. And you can see this one has had quite a lot of custom information inserted into the part itself. So there's information such as who drew it, so drawn by has been inserted in there. There's information such as that description that we saw that was being used in that drawing. So if we wanted to put a new value in here, let's say we were putting a secondary description, you might type in this description 2, and then you could enter whatever you needed in here. For bearings, and then maybe put the spec of 2 bearings. You get the idea. So you can store data and attach it to the actual part itself. And you can see in here a property name has been created for the material and another one for the finish, and they've been populated, so they get stored inside the actual part itself. And then again, what that is promoting is that the parts are driving all the downstream activities. So the drawing would be one of those downstream activities. So that's how you populate these values in the drawing format. I think the last thing that is probably worth looking at is the problem that we had when I tried to just add a sheet, and the system quite rightly said the sheet format that's been defined in this drawings template can't be located on this system. And that's because this drawing and its sheet format were created on another installation of Solidworks. And that sheet format that's been specified in this drawings template isn't available on this system. So that is why I had to take a copy of that existing sheet. So I got round that problem when we were creating this sheet number 2 by just saying right click on sheet number 1. I know that there's a sheet format already stored in sheet number 1, and I'd just like to paste a copy of it. Now the downside of that is it copied all the views as well. So all the views and dimensions from sheet 1, I didn't want any of that. I just wanted the sheet format. So that was a workaround. Now let's say in the future I decided this was the sheet format that I wanted to keep reusing for lots and lots of my drawings. I could then save this sheet format on this installation or somewhere on this system. So the way that you would do that, when you've edited your sheet format, got it looking as you want, you can then just quite simply go File, Save Sheet Format, and it won't save those drawing views, it will only save the sheet format itself. And then give it an actual name, give it a location on the system that you want to locate it at. Now whether that's in the default Solidworks sheet format folder, you could do it that way, or you can save it in a specific folder for the drawings that you're going to create. But you can save that sheet format, and then the next time I pull this drawing in and want to create a second sheet, if the system still says I can't find that sheet format, you can point it at that sheet format on your system. You can say there's the sheet format, every sheet that you now create, use that format. So yeah, I think that's the conclusion of this particular tutorial. We've looked at a little bit of how you might set up some part drawings, a little bit of how you might edit sheet formats, how you might link some of these values back to the actual part custom properties, and how it's best to set up tolerances within the part itself rather than trying to add them to the drawing, and potentially breaking the link between the definition that you model in the part versus the definition of the manufactured part. It's best, if possible, to get everything driven by the part model itself. Don't add extra information in at the drawing level that isn't represented inside the part itself, because you're breaking that dynamic link then.